So we set the scene for S2s predictions in the first part. Here we are moving into the second part, which is called Sources of S2s Predictability. And of course the poster child for S2s prediction has been the Madden Julian Oscillation. This is the historical seminal figure that Madden and Julian published in 1972 after finding some very clear signatures of certain spectral bands from data that they had at the time from islands in the tropics, and of course it didn't get noticed for a while, and then it has taken off, and now it's got a huge community. And the role of MJOs in low frequency climate modes, and then feedback of the climate modes onto MJOs, also, and of course S2s predictions are all building towards a nice story. We'll kind of go through just the basics here. If you want more on MJO in general, I have a seminar on my YouTube channel, and I have part of the tropical dynamics course. There is some details there as well. This figure is basically showing a typical propagation of the MJOs eastward from the Western Indian Ocean sector. So you can see here the longitudes going from the Atlantic sector into the Indian maritime continent, back into the Atlantic sector. And here we are looking at a sequence of events. So it's starting here, the convective phase in the Western Indian Ocean, where sea level pressure is low. So there is convergence, rising motion, deep convection, raised geopotential height, divergence at the top levels, and then subsidence ahead of it with high sea level pressure. And then this thing begins to move eastward, and you can see that the pressure signal moves ahead of the convection because there are always waves involved. This heat source in the tropics generate Kelvin waves and Rossby waves, and there is low level convergence associated with that. When you get into details, you have to look at the easterlies and the mean winds on which they are acting. So these are MJO timescale, MJO associated wind anomalies, and behind you have westerlies adding on to the background winds, and those are invoked to explain what can cause this propagation eastward and why the convection moves eastward. And it turns out that pretty much convection in the tropics is hardly ever stationary. It's always being moved around by waves and background states and so on. So you see the idea here. So the convection is moving, the sea level pressure signal is getting ahead of it, and then once it's transitioned over from its original phase, you have subsidence over there, and you have high sea level pressure and low sea level pressure ahead of it, and then so on. So you cross from Africa into Indonesia and South America, and then back again. In general, the convection, as it goes past the dateline towards the eastern Pacific, the mean sea surface temperatures are colder, so convection doesn't persist, but the circulation does often, and then crosses over the South American continent into Atlantic and back over the Indian Ocean, Western Indian Ocean. But not all of them have this full circumglobal propagation. Some of them pop up in the middle, die away in the middle, and so on. So we will see later on that there are some that are coming back and regenerating. They are called secondary MJOs, and then there are some that are originating from scratch. They are called primary MJOs, and then there is also evidence that extratropical perturbations are triggering the convection that leads to a genesis of an MJO and so on. So without getting too far ahead, this is another way to look at it. So you are looking at the jet stream up here, and you get some sense that maybe there is some extratropical tropical interactions happening here. As some of you may know, in the upper atmosphere, the jet stream communicates with the tropics in the so-called westerly duct, and then the signature propagates westward and then goes back out to the extratropics. But again, without getting too far away from the MJOs themselves, if you look at the OLR associated with this, positive OLR are the dry phases, and when there is deep convection like this, the temperatures above are reduced because of the rising motion and cooling of the air parcel as it rises, and cloud top temperatures are colder, so the OLR is negative anomaly with respect to the background. So you have convective phase there, and you can again see it's going through, and phases are being mentioned here. We will see what that is here. So you can see that this is phase 1. Now we are looking at precipitation in millimeters per day associated with the MJO. So typically you have to filter in the intraseasonal band to get these MJO related signatures, and the band pass filtering typically goes from 20 to 100 days and so on. People change that a little bit based on various logic, but the convective phase is over here in phase 1. Phase 2, it's moving towards the eastern Indian Ocean. Phase 3 over the maritime continent. Phase 4, 5, 6, 7, 8, and so on. And you can see that the convective phase doesn't last into the eastern Pacific, as I said, but you also see the mix of other signatures here. The ITCZ is clearly seen, the SPCZ, and there is evidence that some of the MJOs actually do not cross the maritime continent over here. They are detoured southward and go on into the western Pacific here, affecting the South Pacific convergence zone, and there are such details. This is a very multi-scale system where the background Walker cell and Hadley cells and MJOs are interacting with each other, and the heat source associated with the MJO is setting off Rossby waves, which are going off away from the equator and affecting all sorts of things well into the extratropics and high latitudes. MJO phases also have an impact on cyclogenesis because of the convective activity and the favorable vorticity, shear, vertical velocities, mid-level moisture loading, and so on and so forth. But what is very clear is that Madden Julian oscillation has this eastward propagating convective phase, and it is in the so-called sub-seasonal band, which is less than a season, so less than, let's say, 90 days. And this is the typical structure. We will see more of this as we go forward. So you have a convective phase here, convergence into it, with easterlies ahead of it, westerlies behind it, and then rising motions, divergence at the top, waves associated with that, which we will see, and then there is downward motion ahead of it, so a dry phase ahead of it. Okay, so that's kind of the brief background. We will add more details and more background as we go forward. So convective phase, waves, convergence at lower levels, divergence at the upper level, and dry phase ahead of it, and eastward propagation. Not all of it are fully explained, as we will look at the theories, which means there is not one theory, there are multiple theories for MJO, which means it's not completely understood, if you will. So we will look at some of those things as we go forward.